Hi everyone, am I audible to the last bench? Okay, so I am Zeel. I am a 6th year PhD student in Sustainability Lab working with Professor Nipun Batra, and today I am going to present a topic called active learning. So as we all know, with the rise of supervised learning, there is a huge increase in amount of data sets that we have, but they are not necessarily labeled data sets, right? For example, if you take an example of speech recognition, we have thousands of hours of speech data sets which are available, but they are not labeled, which means that I don't have a one-to-one mapping between a speech clip and corresponding text. So if I need to train certain model based on this data set, I would need the labeled data set. Now, if we employ people to annotate this data set, it is a resource consuming process. So we have to be more efficient in the way that we do this to make our models better and better with lowest possible resources used. Another example would be, let us say, something like human activity recognition. So in such tasks, sensors are attached on different parts of human body, and then we are trying to classify different activities that human beings are performing. So here also you will have a lot of noisy sensor data which is there, but you don't have annotations for them. So can we do something better to quickly annotate such data and get our model perform better with lowest number of samples? So first let me ask you, like, do you have any thoughts of like how can we achieve something like this? Let us say you have million samples of any task that you can think of. How would you go about efficiently improving your model without labeling all the million points? Any thoughts, any ideas? Sorry? Yes, that's the good point. Like if we can cluster them into smaller groups and then let us say we assign a label for that particular cluster. That's one way. Any other thoughts? Okay, so we can use this thought process called as all the samples are not equally important, right? Which means that I may have million points, but all of them are not contributing equally in improving my model. So if I can pick certain points which are improving my model in the best possible way or the fastest possible way, then I would be needing least number of annotations to make my model better. Right? To illustrate this point, let's see an example. So all of you know a classifier called support vector classifier, right? Let us say you have a binary classification problem like this, where we have two classes marked as the orange and blue points here, and decision boundary is something like this. But for now, let's assume that you don't have these decision boundaries, and all these bigger dots are the only points that are there in your train set. Now, I would like you to focus on point A and point D. Can any of you say that which point is more important in defining the decision boundary correctly? Point A or point B? Point B, right? Why? Right, because it is near the decision boundaries. So I think all of you would agree with me that if I pick points which are close to point A or point C, they are not going to help me improve the decision boundary. But if I am choosing more points closer to the decision boundary, then I would be improving my models as quickly as possible by adding minimum number of points. Right? So this is just one illustration to say that all points are not equally important. So then we need to have some kind of metric, some kind of method so that we can find out these important points and incorporate them into our model. So that was an example of binary classification. Now let us see the confusion in digit classification. So all of you know the MNIST dataset, right? So if you fit a model on MNIST dataset, we would get a confusion matrix looking something like this, right? So now if you look at this confusion matrix carefully, and if you look at let us say digit 5, then we see that digit 5 has the predicted digit, sometimes it is as 3 or sometimes it is as 5. So it means that the actual digit 5, the model is confusing it between digit 3 and digit 5, right? So looking at this confusion matrix, you can say that model is more confused about classifying certain digits compared to the others. So then you would agree that if we show more examples of such digits which model gets confused about, then we will be able to improve model quickly, rather than, let us say, randomly choosing all the images and labeling them, right? So again here the same point comes, that how can we identify such images so that we can label them and improve our model as fastly as possible. This was classification. Now let us also see a regression example. So this is a kind of data set we are looking at. It is a noisy sine curve where the underlying function is sine and we are adding some random Gaussian noise. Now there is a model called Gaussian process. You don't need to worry about it. You can just think like it is a polynomial regression model which also provides you the uncertainty around its predictions. Here the dotted line shows the mean prediction and the shade shows you the uncertainty. All the black dots are the training points to fit the model at this position. Now you can see that model has higher uncertainty at certain points and it has lower uncertainty at some other points. Now similar to our earlier support vector classifier example, here also we see 4 points A, B, C, D. Now can you again think which points, if I add to my model, they will improve my model by the in the best possible way? Will that be point A and D or point B and C? Any answers? A and D, right? Why? Because intuitively you might think that they are far away from the training points and they are located at regions where my prediction is also bad, right? So we can click and see that what happens if we add point B and C. So we can see that model is still not getting very accurate prediction near point A and point D regions. But if we add point A and D, we are overall doing good job at the entire data set, right? So what did we do here is that we again made an intelligent choice of data points so that our model gets better with minimum number of annotations. Now coming to formally defining what is called as active learning. So in an active learning process, you have some initial data set and you have a machine learning model. And you have a huge pool of unlabeled data set for which you don't have any labels. Then you employ certain functions called as acquisition functions to smartly decide which points to pick from these pool points and add them to the train points and then retrain your model so that your model gets better and better with minimum number of annotations. That's the entire concept of active learning. So till this point, anyone has any doubts, any questions? Okay, so let's continue. Now to check if our active learning method is working or not, we have to compare it with some baseline. And in this case, we can compare it with random baseline, which means that out of, let us say, millions of unlabeled points, if I randomly pick samples and annotate them, how my model improves versus if I intelligently choose the points, how my model improves. If I compare these two things, then I should be able to see that when I use active learning, my model is improving better than random, right? So that's how we will use random baseline. Now there are different scenarios in which we use active learning. First is called as membership query synthesis, where you have an underlying distributions. So nowadays this is easy to understand with LLMs, that when you query an LLM with a particular prompt, every time you get a different sample, right? So your LLM is a generator which generates different kind of texts for you, and then you can evaluate this text through your acquisition functions and check that what's the value of that acquisition function. And you can define some thresholds that if it is more than certain threshold, maybe you should annotate that sample. So that way, even though your model may randomly generate samples based on the acquisition functions, you would be able to apply a filter and only choose good samples to train your model further. Another scenario is called stream-based selective sampling, where you have a stream of data coming to you, and then when a data point arrives at you, you can take a call based on an acquisition function if you want to annotate that or not. And the third method, which is most prevalent in any supervised machine learning method, is that you have the entire data set with you, which is unlabeled, and then you would like to apply acquisition functions on top of them and selectively only label few data points out of them. That is called as pool based sampling, and this entire unlabeled data set is called as pool data set. Now in pool based sampling, there are mainly two strategies. One is called as uncertainty sampling and the other is query by committee. We will look at them one by one. In uncertainty sampling, the intuition is that we want to leverage or we want to exploit it that is present in our model itself, which means that if my model is saying that I do not know much about this particular point, then I would like to annotate that point and include it in my training data set. Let us see that with an example. So in this example, I am showing three different digits from the MNIST data set. If you focus on the first row, it is just showing you the raw data set sample 2, 0 and 5. If you focus on the second column, second row, then it is showing you the probability distribution from a classifier. So this plot, which is just below digit 2, is showing that what was the predicted probability between digit 0 to 9 for this ground truth sample 2. Similarly, we have it for 0 and we have it for 5. In the last row, we are demonstrating three different acquisition functions which we can use to smartly select different points from this data set. So let's see them one by one. I think every one of you is familiar with entropy. So entropy is also a measure of uncertainty. So when you compute entropy, if you have higher entropy, which means you have higher uncertainty, and you should choose that particular point to do the annotation. So among these 3 points, we can see that this digit has the highest entropy, which means that when we will do the active learning process, we would choose this point and we will annotate it. The second strategy is called as least confident method, where we just look at the digit where we have maximum probability prediction. So if you look at all three examples here, though the ground truth digit is 2, we are having maximum probability for digit 1, which is 0.24. For the second one, we have it for digit 7, which is 0.31, and for the third, we have 0.29 for digit 3. So among all these three, for whichever point we have the minimum number, which is in the first case 0.24, we are going to select that particular point to do the annotation. So I think entropy was straightforward, but this might take a bit to understand. So anyone would like to comment that, like, why are we choosing a sample where the maximum probability is minimum across all the samples? So that is because if your maximum probability is minimum, then the remaining probability is distributed across the remaining digits, right? And which means that your model is more confused. If it was not confused, it would have assigned probability to one particular digit and very less probability to the remaining ones. So that case we would call as more confident. But here model is not confident and it is the uncertainty in the model. So that's why we would like to choose that particular point. Now the third method is called as margin sampling, where we look at the difference between the first maximum and the second maximum probabilities. If this difference is minimum, we would like to pick that point. Why? Because it shows that if the difference is minimum, then my model is confused between two digits while it is trying to predict something. Right? So I think this is also intuitive. Among these three strategies, is anyone has any doubts? Yeah. Okay, so I think I would repeat the question for the audience, that what happens when in cases where the maximum probability is for the wrong digit, right? Is that the question? So at the time of active learning, you don't really know if it is for the correct digit or not, right? Because you don't really have the labels for these pool data sets. So we don't really have that choice to rather like choose for the digits where the predicted digit is correct or not.
Okay, so the pool that you have, you don't have that label.
Right, right. And that's why we are using these acquisition functions to try to pick particular sample and then annotate that.
Okay, okay.
So only those samples we will show to some human annotator to like give the label for.
It makes sense.
Yeah. Any other questions? Okay. So if not, we will move forward. So this plot just shows the actual active learning process, where in each iteration we were choosing a particular sample and giving it to Oracle to do the annotation, and then we include that point into training data set, we retrain the model, and then we repeat the process in each iteration. So here you can see that when we do random sampling, which means randomly pick the points and annotate them, over 100 iterations, which means over 100 annotations, our model was able to reach up to F1 score of around 0.7. But when we used other strategies, we were able to reach around up to 0.8. So there was a gap of performance of 0.1 between the random and the other acquisition functions. Right? So now you can see that when you use strategies like active learning, using the same amount of annotation effort, you can make your model better rather than just doing random sampling. This was in the classification case. Similarly, we can see in regression. We saw this Gaussian process example earlier. Here it is much more simpler, that at every point you have a prediction and you have uncertainty. You simply need to pick a point where you have maximum uncertainty. Here uncertainty is in terms of the standard deviation, because the Gaussian process model is predicting a Gaussian distribution at each and every point. Right? So if I look at this particular plot, in the left hand side you see this red dot where there is a maximum uncertainty, which is shown by this bar. So when I go next, that particular point is annotated and added to my training points. In the random, any random point will be chosen. So if we continue doing this process, on the left hand side you would see that we are quickly capturing the original trend of the data set, and that's not happening on the right hand side, because right hand side we are just uniformly randomly choosing the data points. We can see that just after 6 to 7 iterations we have almost fitted the plot very nicely. Right? So this is how we can do active learning in regression setups. For that you just need to have a model which can provide you a measure of uncertainty for your data points. Moving to the last part, which is query by committee. In this strategy of active learning, you have multiple members in a committee which give a vote for a particular prediction. In case of classification, you can have different models which give you predictions, or you can have same model with different hyperparameters which can give you the predictions. And then we take different votes from them. For example, let us say if we pick a particular point and I have 3 models and 3 of them are classifying this into different classes, then we can say that okay, all the members in committee are not agreeing here, and that is called as maximum disagreement. So in query by committee, we will pick samples where there is a maximum disagreement among all the committee members, right? And here we have chosen iris dataset and support vector classifier with different hyperparameters C, 0.5, 0.1 and 10. And here we can see that in each of this classifier, we have different kind of decision boundaries every time. So when we find a point where each and every classifier is giving different prediction, then probably that is the best point to annotate for. Following this strategy, we can make our model better and better with lowest number of annotations. Finally, we are just doing a comparison between the query by committee and all the other strategies that we saw. And in this particular case, QBC is performing best among all the other active learning strategies. But that's not generally true, right? As we call as no free lunch theorem in machine learning, that as your data set changes, you may find some other strategy works best for you. Or sometimes you may find cases where even random is the best and your strategy is not able to beat that, right? So with that, I think I have covered the basics of active learning, and I would like to invite Suruchi to walk you through the lab.
Okay, I think that you have grasped the basic of active learning, and now moving on to the hands-on part, I would like you to uncomment this first line. If you doesn't have the necessary libraries installed, else you may skip. For this hands-on, we are doing the classification task, and the data set that we are using is the digits data set. Quick introduction about this data set. It has around 1797 samples, and it has a feature vector of 64. That is, it is an 8 cross 8 pixel grayscale images of digits, and previously we studied that in pool set we don't have labels, but since it is a lab setting and we already have the labels of the data set, so we don't need any human annotator here in the loop. Firstly, in this cell, I have installed all the necessary packages and libraries. And for the classification task, I am going to use the MLP classifier. And this is just a basic visualization of the data set, how the data set looks and how the digits are represented. As we all know, for classification tasks, we have to split our data set into two sets, train set and test set. I have done also the same. But in active learning, we have an initial small subset of labeled set, a pool set and a test set. So for doing the same, after splitting the train set into 1297 samples, I have resplitted it and I have taken the initial label set as only of 100 samples, which means I am starting my active learning loop with just 100 samples and see how my model predicts in the test set. And iteratively, I will add one samples in each iteration to this initial label set and see how my model performance improves. Zeel has told us about the acquisition function that we can use in active learning. Here, I have used 3 acquisition functions: random sampling, entropy, and margin sampling. For random sampling, I have used NumPy class for choosing the random samples from the pool set. I have passed the parameter replace is equals to false because I don't want the samples to be repetitive in each iteration. Moving on to the entropy sampling. As we all know that entropy is the measure of the uncertainty or randomness in our data set. Say for example, if I have a data set with 2 samples, sample A and sample B, and 2 classes, class 1 and class 2. Our model predicts sample A with probability of 0.5 belonging to class 1 and probability of 0.5 belonging to class 2. While on the other hand, our model predicts sample B with probability of 0.7 belonging to class 1 and 0.3 belonging to class 2. So, what do you think? In which sample is most uncertain, or which sample do we choose for our next iteration? Is it sample A or is it sample B? Sample A. Why? Yeah. Sample A is most uncertain here in this case. Why? Because our model predicted sample B of belonging to 70% probability belonging to class 1. That is, it is more confident as compared to sample B, where it predicted both the classes with equal probabilities. This is what the main aim of entropy is. The same function is implemented here in Python. First, I calculate the probability scores from the pool set of the samples, and then since entropies use a different dimension, so that's why I have transposed the probabilities, and then I sort the indices and take out which is the most uncertain sample from the pool set. Next is margin sampling. Earlier told that margin sampling means it takes the top 2 classes predicted probabilities, and in these top 2 classes, which sample is having the minimum difference between predicted class 1 and predicted class 2, and that sample will be taken out. Like for example, in our previous case where I have a sample A with 50-50% of class 1 and class 2 and sample B with 30-40%, 30-70%. So margin sampling predict that top 2 predicted class of sample A will be of least difference. So it will predict as sample most uncertain in this case. For this case, the probabilities are calculated, and then top 2 probabilities are calculated using np.partition function, and which sorts the probability scores, and then we take in ascending order, and then we take the last 2 probabilities, that is the most top probabilities, and then we take out their differences and calculate the indices which are most uncertain. For every model, we have a baseline to compare. Similar is in the case of active learning. We compute baseline here in 2 cases. First, we have only an initial label set of 100 samples. We compute the baseline of our model performance like in just 100 samples. What is the accuracy of our model? Next, we take all the training set and then calculate the accuracy, and then check. This is the threshold that our active learning acquisition function has to cross by or has to reach. So then we can compare that with this minimum number of samples, this strategy is best and is closer to the threshold. Here is a demo. Any doubts? No? Okay. Here is the demonstration that will go you through the active learning loop. Initially, we have a label training set that is 100 in our case, and then we apply our machine learning model, do prediction, and then we iteratively select samples from the unlabeled pool set and give it to the annotator. In this case, we already have our labels, so we skip the annotation part. But in production setting, we don't have this. So we really require a human annotator or other annotator for this. And then we add this labeled sample in our training set and then repeat the loop again and again so that we can get a desired performance. The same is explained through the code. First, I have created copy of code so that we can avoid any changes in the original data. And then for classification task, I have implemented the MLP classifier with desired parameters. And then for adding the sample query points in each iteration, I use npick.concatenate function and add the label point to the pool set. And removing those label points from the pool set, I have used a mask function. Initially, all samples have mask 1, but the samples that they are in indices, means that are chosen, are masked as false, which means that when I rerun the iteration, then this sample will not be chosen again. Next, we have created the list of strategies that we are implementing here. I have run this experiment for 500 number of iteration, and in each iteration, I have sampled one data point, which means that in 500 cycles, I will take out 500 samples. For random sampling, I have taken another variable explicitly, that is number of runs, and is set it into 5. And then I repeat the same procedure of the active learning loop for this 5 number of runs. Can you explain me why I am repeating this random sampling 5 number of times or number of runs time?
Every time we did this vector equation, so we want to know like what is the variation.
Yes.
And finally the average of distribution of patterns.
Yes, correct. Since, as the name suggests, it is random. So it is not sure that every time we run random experiment, we are explicitly likely to get the best sample in each run. So we run the experiment multiple number of times so as to average out the differences. You can see this in this also. Like first time when I run the experiment, I get a 93% accuracy, but second time I get a 90% accuracy. And this accuracy is variable. So that's why I have run this experiment multiple number of times and then plotted the variance and the mean in the graph. It is plotted as a standard deviation here. Next strategy is entropy. And I have also explained you the code, and this time I am just calling the function and then plotting the curve, and this is the curve. So you can get that around, this is the active learning iteration, and in each iteration I am sampling 1 point, that is 1 sample. So you can see that around 250th iteration I am able to get a desired performance of our model, which means that when I have in train set I have 1297 samples. So the similar accuracy is achieved with around 250 queried sample by entropy sampling. So isn't it this cool? Like with just 250 samples, we are able to get the same accuracy with, as compared to the same accuracy we get around 1000 samples. Similarly, I have plotted the curve for margin sampling, and this is the overall curve that helps you to distinguish which strategy is best. As Zeel suggests that this active learning strategies are data dependent. You might have to experiment with different strategies to get out your best one. We have another Python library that is built specifically for active learning, that is ModAL. This library is built on top of the scikit-learn, and it is specifically designed for querying different samples with various uncertainty strategies. You can visit out here to get the more detail about this library. What I am going to use in this tutorial is their uncertainty sample function. This has various sampling strategies like entropy sampling, margin sampling, uncertainty sampling. So you may visit out that, and I am using active learner class here that is particularly used for classification like task and can call various uncertainty sampling functions through it. You can use this pip install if you don't have this library already installed, and like previously, I would import all the necessary libraries, load the data set, split the data set into train, test, and pool, compute the baseline with only train accuracy and train plus pool accuracy. Then I run the active learning loop with similar number of queries and similar 1 train examples per iteration. And this is the plot that I got. Here I have called the active learner class, and the strategy that I have implemented here is the entropy strategy. Here, query strategy entropy sampling. For this, I have already called in from modal.uncertainty import entropy sampling. This is important. Next, moving on to the hands-on, I would like you to draw the similar plot through ModAL, but by using margin sampling technique. Similar curve I have plotted with entropy sampling. I have provided you a basic structure. You just have to call the libraries, use the function, and then see how the model performs.
Meanwhile, you can ask your questions to Suruchi.
Actually, my question is because I am also working on this type of algorithm part, so I also selecting the data points. So for in algorithm parts, so how your data points you are selected is diverse. So how you manage the diversity in that algorithm? Because you in mathematically part you are using any distance formula, like I am using the L1 norm distance or L2 norm distance function. So how you maintain the diversity here?
Okay. So in active learning, there is two kind of parameter that we have to find out. One is diversity, and other one is like this selecting out the most uncertain sample. Uncertainty and diversity we both have to maintain. Since it is a simple data set, I have not taken into account the distance factor here, but as we go into production setting, we have to take out samples from various regions. Like in satellite imagery, in which our lab works, I am also working on active learning, where I have to take out the samples from different region on brick-kiln detection. So one way is that I have to take regions from different geographies, so that the model can understand, irrespective of the terrain, that here is the brick-kiln detected, and in Plateau region how it looks like, and in other region how it look like. So in real life production setting, we have to balance both uncertainty and diversity. For this we have other complex function that maintains both. So but here it is just for hands-on. I am using a simple data set, so that's why I focus mostly on uncertainty here. Okay.
So hello, my question is like active learning is only for like labeling the data points, and so after that, do we have to apply supervised learning too? No.
Like it is mostly for selecting out the most uncertain sample. After that, you will apply your algorithm and on top of that. But the main motive of this is to select the minimal number of samples that will give out the maximum result. Okay.
So like, does active learning have any other use cases other than labeling the data points?
I think that's our next talk, just after this. Yeah, so I think in interest of time, we can go to our next talk. Hello.
Oh. So am I audible at the back? Thumbs up. Here. Fine. So it was a long session till now. I think you guys were awake, asking questions about other applications of, uh, uh, active learning. But first, I'd like to ask a question: what is active learning according to you? So there were two people telling you about active learning. I think you should have gotten it by now. Anyone? Sorry?
Reducing the reducing the labeling cost of that data.
That's actually one application of it, right? What is active learning?
It is sampling the record data.
Okay, let's get back to you.
So what I got through the talk is like using least amount of samples, how you can perform better. So sample efficient techniques, like how like we humans are like essentially very active learners. We use very least amount of examples to learn. So I guess that's why the name
Okay.
active learning. We need only 2 to 3 examples to distinguish between cat and dog. I suppose so.
Fair enough. Yes, you were saying something? Okay. So this is one such application, air quality station deployment using active learning. And this is, by the way, not a made up problem. This is one of the key research areas of our lab, and I happen to work on this statement as well, right? So what is the motivation behind placing air quality stations across, the country? Why would we even want to place the sensors? Why is it a problem, right? So air pollution kills around 70 lakh people every year. If that is not motivating enough, 17 lakh fatalities occur in India alone, right? So as Professor Udit in the second session today told, we can improve something only by measuring it first. So we want to accurately measure the air quality, right? So currently we have 558 air quality stations across the country, India, and the demand is around very huge, 4,000. But the problem is, what is the problem then? Why can't we just place 4,000 stations? Why do we not want to place more than that? Why can't we just place a station at every nukkad or every choraha, every gully of your town? Yes? Yes. So they cost millions, right? So we do not want to, burn that much. Another thing, the pollution is not like the same everywhere, right? You must have noticed at Delhi, at places like the northeastern belt, the population and pollution both are generally high, right? So at those places, we want to place more sensors. We want to be more accurate at those places, rather than placing sensors at places where the pollution is less, like Ladakh, let's say, right? So you have seen this diagram before. I'd like to contextualize with our problem. We choose one of the points select queries from. Okay, so we select a query from this unlabeled pool, and we label that, right? So in this, what we'll do is, we have some points where we can place the sensors. We'll select one of the points, and that goes inside our training set. We perform this loop again and again to place one sensor at a time up to n number of iterations, right? So just like earlier you had seen, you had one. Oh yes. Okay, sorry. Should I go back?
You want to have air stations, right?
Yes.
So you said that demand is of 4,000.
Yes.
Now you have the location of 4,000 things, right? The places where you need them.
No.
Then what do you have?
We have the complete Indian grid, right?
Okay.
So across any place or across India, at any position, I can place the sensor. That's a difficult optimization problem, right? I want to place sensors accurately, minimalistically, such that I get the maximum accuracy, predictive accuracy, right? You're getting what I'm trying to say?
Okay, so you are saying it is a very difficult optimization problem. So that's why we didn't pose it as one. And that's where we're going to this active learning thing.
Yes.
Okay. And okay, so and then you are using these functions that he was talking about, and then you are
we'll come to
getting
that.
one point.
We'll come to that.
Okay.
Okay. Any more questions till now? I'm happy to take. Okay. So earlier, just like earlier, we also have some train points. Just like earlier, we had some training points, some pool points from where we actually label this, where we want to label, right? So if you look at the diagram on the left hand side, these are actually CPCB sensors which are currently placed across India. These are 555, 540, whatever sensors they were there, right? So these are there many. These are the actual positions of current sensors, right? So this happened to be the same analogy as your the training set, right? So this is your, what was the other set? Pool set, right? So here, these are the points where you can place the sensors, right? So you can imagine them as, you know, as very nearby points, like just very high resolution up to 10 kilometers or 1 kilometer, let's say, to place sensor at any of these, you know, grid, right? So these are your pool points where you can place the sensors. But my question is, where do we place the next sensor? Till now, I haven't told you any strategy. What do you think? Any heuristic technique that you can think of? Gradient distance, right? Okay. Between what?
Between the sensors that are operating.
Yes. Very good. Any other? That is actually one of the strategy. So the same thing that he said, we place the sensors as far apart from, okay, this is, okay. So as far from each other as possible, right? So this is a heuristic technique, right? Any other technique, by the way? Any acquisition strategy from any previous, you know, that you remember? Okay. Entropy, the same thing, right? So in this case, what would be our entropy? Entropy would be, let's say, as he said, in regression problems, we have models that predict both the output as well as the standard deviation or the variance, you know, telling us about the uncertainty of that output, right? So this X star is the point where we want to place the sensor. So next point where we want to place the sensor. Out of these pool points, I select that point which has the maximum entropy. Any confusions? No confusions? Okay. Oh, yeah. Okay, that we'll come to that. Okay. But just for now, you can assume that we have at each point the output as well as the predicted variance, and you can choose the points accordingly, right? Okay. The second line that you see of the formula, this is just another form of this, right? If you break this down, you'll see if you remove all the constants, you'll come down to this sigma square, which is this, the variance, right? Another strategy, which would be mutual information, right? Don't get intimidated by this whole big formula. Let me break this down for you. So again, this X star is the point where we want to place the sensor. Out of these pool points, which we have, this is the entropy of the current entropy that we get at all the points, right? So XS, just to be clear, XS is the output at all the points. Okay, the complete search grid, as many points as you can fit, can do the test on that, right? So this is the entropy on all the test points. Anybody would like to comment on this term, which is very similar to this, just some additional terms? Okay, any other try? Yes, exactly. Thank you. Thank you. So this is the current entropy, and what would be the entropy of the system after adding this particular point from the pool, right? So we select that point which has the maximal reduction in the entropy. Any confusions? Clear? Okay.
Very good. There is a question in the last slide.
Okay. Yes.
So, like, I would like to ask, like, in the second formula that you see, second term of the formula, you see y also there, right? And you are iterating this over all the points in the pool set. So how would you get the y? X is the location that we have everywhere, but you don't really have y, which is like the observation at that point. Any comments? Yeah, you can answer.
Coffee from my side if you answer. Okay. So this, as he said, this X is the point which is the pool point that we added to check the entropy. This Y we don't have, right? But what if I use this Y as the prediction that my model gave? Is that a similar replacement? There is some bias, of course, but we can use that, right? While placing sensors, we won't have actual data, right? So we'll have to use some kind of, so we'll use model's output in place of Y, right? So it would be Y bar. So you can just, this is just notation you can understand. Again, back to the question, how do you get the uncertainty from neural networks or any models, any machine learning models? Very simple. Okay, I'll give a hint. Okay, so what if I tell you I can get this from just by using some dropouts? No, you understand what dropouts are, right? Okay. How can you do that? Usually you do use dropouts while training, right? While testing, you remove that. What if I keep that during test time also? Now, how can I get the variance? Okay. Anyone? Yeah, thank you. Exactly. So what if this is by the way called MC dropout. So what you do is with the same network but with different dropouts. So with run this multiple times. So each time different neurons would get cancelled, and each time you would get different Y. So Y1, Y2 up till Yn, right? You can average them or to get the mean, and then you can calculate the variance across them, right? Sounds easy. How about using a deep neural network? This is not deep, but a neural network for that, rather than predicting just one value, you get two values, mean and standard deviation or variance, standard deviation, right? Okay. Okay. We come to our model. This is what is the most interesting one. Don't get intimidated again. So again, this is just a neural network with an encoder-decoder architecture, right? Again, the output is same, mean and standard deviation. So some neural network that gives me two outputs, mean and standard deviation, right? And in between we have some encoders, some decoders and something happening, but this is the core objective, right? So in the input, what I have is the current data that I have for the sensors, x1, which is the latitude longitude pairs of that sensor location, the corresponding y1, which is the PM 2.5 value at that location, and we pass that to the model. We get the output as, at whatever target point we want. So this, this xt is the target point where we want the prediction. So we could pass that to the decoder and ask, hey decoder, what is the output for this target point? Right? Could get that? Any questions? I'm happy to repeat. Clear? Okay. Yeah. Sorry? Okay, that's a good question. Okay, I'll give you a basic overview of that. Rest we can take offline. So, in generally, neural networks, you see backpropagation happening, but how do you backpropagate through something like this, right? Mean and standard deviation, something like that. So, since the output is a mean and standard deviation, so eventually what you have is a distribution, right? You parameterize a distribution using a mean and a standard deviation, right? So you have these two things. You can define a distribution. You have a distribution. Given this distribution, what is the likelihood of getting this, the correct value? Okay. Okay. The negative of that log likelihood would be my loss function, right? Then I backpropagate. I'll get these two things as mean and standard deviation. How neural network does that? Okay. So this is one of the case studies. We tried this experiment. This is the data that we used is Washington University's simulated data. This is not actual data. This is simulated through various techniques like machine learning models and satellite imagery, right? So we use data of very low resolution up to 0.1 degrees. Could get that because they are just estimated values, not very correct values, right? But generally the trend remains the same, so we could use that. Now these are the active learning results. If you see across various strategies, we get different reduction in RMSE, right? So choosing a smart acquisition strategy could lead to fast reduction in our RMSE or whatever goal we want to achieve, right? If you look at the baseline or a random line, you could see far away from that. Placing sensors randomly could lead to, this much difference, right? So this is a visual output. If you look at the green points, these are the points that are chosen by maximum variance strategy. We choose points where the variance is maximum, right? One thing that you would notice is that these points are all at the border. Do you want your sensors to be placed at the borders? No. Eventually the coverage you want to increase, but this is decreasing, right? So another strategy, which is joint entropy. You see the placements that it performs is generally not at the border, right? So you want to increase the. Sorry, you want to ask something? Okay. Right. So this is another visual result. On the left hand side, you can see the ground truth. This is the WUSTL data, ground truth that we had, right? This is the CP sensors location. So the model's prediction using these points. So when these black points were given as the input to the model, this is what the output was, right? After doing active learning, you'd see this is these blue points are the points that are chosen by active learning, and this is the output. You see that I don't know if this is even visible. So these two are quite similar, right? More similar. Okay, so that was all. Any questions? We are happy to take for anybody.